Welcome back, everyone, to MAE170. This is lecture 13 in week number 8. So this lecture is going to be slightly different than usual because of what I wrote in the announcement on Canvas. So without further ado, let's move on to today's lecture. In today's lecture, we're going to see the frequency response methods, and in particular, we're going to analyze the so-called Bode plots. Most likely, you've already encountered the Bode plots in your studies in MAE106. However, if this is the first time that you hear about them or you see them, well, no problem. We're going to analyze them in depth. Everything that I will be talking about is in chapter 8 of your textbook. So what's the deal with the frequency response methods? Why are they called frequency response methods? Well, here the key word is frequency. And this is because the inputs that we will consider are harmonic inputs. So far, we've seen impulsive inputs, step inputs, ramp, acceleration inputs, but we never really took a good look at harmonic inputs. Harmonic inputs, as we can see here on the left, well, they are functions that are characterized by an amplitude, here a 0, and then a frequency omega. So it's just your sine or cosine function. Here I just chose sine, but it's completely indifferent. You can choose also a cosine function. Sine and cosine functions are the same, just transposed by a phase of 90 degrees. All right, so when we consider these kinds of inputs, that is harmonic inputs, then the output for a system that is either stable or marginally stable can only be of 3 kinds. Case A, this is the first option, when the system is stable, then the output is going to be a purely harmonic function as well. So once again, the output is going to have an amplitude. Here, I'm going to call it AF. And it will be shifted with respect to the input by a phase phi. However, the good thing and very particular thing that happens is that the frequency of this output is exactly the same as the input frequency. So we have that the system oscillates at the same input frequency omega. This purely harmonic function that we're describing as the output happens solely after a certain amount of time. And that's why we focus on the steady state portion of the response. Practically speaking, the steady state portion of the response is achieved when the time is greater than the settling time. Okay, so the second option that we have in terms of output is that we have a combination, a superposition of different harmonic function with different frequencies. One of them being the frequency of the input, and then the other frequencies, which I've called omega and I, are going to be the natural frequencies associated with poles that lie on the imaginary axis. So case B can only happen if our system has poles on the imaginary axis. Case 3, in which, as you can see here, the output just oscillate with increasingly bigger and bigger amplitudes, so it's going to be an unstable response. This happens when one of the natural frequencies of the system coincide with the input frequency. So in other words, if we have some poles on the imaginary axis, let's say at plus or minus 2i, and we excite the system, that is, we use an input that has also 2 poles on the imaginary axis at the same location, then the output is going to just blow up. And that's because it's like having a system with the multiplicity equals 2 for the poles on the imaginary axis, which makes the system unstable. So before going on and describing the Bode plots, I want to show you guys a simulation using MATLAB. All right, so here I want to simulate the cases that I've just shown you, plus a fourth one. So in the script, you can see I just wrote down the basic function to create the transfer function S, and then I create the input. So here, instead of using a function in the time domain, I'm using the function in the S domain, which is much easier to deal with. However, I also referenced it to the time domain for convenience. So the input here, it's sine of 1/2 t or 0.5 t. So in the S domain, that becomes 0.5 over S squared plus 0.5 squared, which is 0.25. I just transform into the Laplace domain the harmonic function. Then we're going to consider 4 cases for the system. We're going to have a stable system. So we have 2 poles, no zeros. Zeros are quite irrelevant when it comes to stability. So we have 2 poles. There are complex conjugate and with real part negative, obviously. Then for case B, we're going to have a marginally stable system that has different poles than the input. So the poles here are going to be at plus or minus 3i. For case C, we have a marginally stable system, but now the system has the same poles as the input. The 2 poles are at plus or minus 0.5i. So the poles of the transfer function of the input are the same as the transfer function of the system. Here, GC is not the controller, it's just for the case A, B, C, and D. So the case D that is not in the notes is just another marginally stable system, but now we have a pole at the origin. We also have here a 0, and you'll see why I've used the same transfer function for an example that we're going to see later in the lecture. But here, the important thing is that we have 1 pole at the origin. So technically, the system is still marginally stable. Well, we're going to see what the response will be due to a harmonic input. So before actually studying the output, let's plot the poles on the complex plane. And so, as usual, I've used the PZ map option. So if we just run the script, okay, I don't know why it's taking so long. All right, so here we can see the poles for the 4 cases. For plant A, that is for the stable system, we have the 2 poles. They are all the way to the bottom and top left corners. So we have the 2 poles at -3 plus or minus 4i. And then for the case B, we have the 2 poles at plus and minus 3i. For plant C, we have the 2 poles at plus or minus 0.5i. So the 2 poles coincide with the poles of R. And then finally, for the plant D, we have 1 pole at the origin, and we also have a 0 at minus 0.5, but that doesn't really matter. Okay, now that we have the poles for our plants, we can go ahead and compute the outputs. So let's do so. For some reason, it's taking forever. All right, here we go. So as you see here, the outputs look qualitatively exactly like I drew in the nodes. So for the stable system, we have an output in the subplot 2 that has the same frequency of the input. It is clearly visible that is the case. However, the amplitude is different. You can see that the input has an amplitude of 1, whereas here the amplitude has decreased to 0.04. And also, well, when it comes to the phase, it seems like the two signals, the input and output A, are in phase. That is, a peak, let's say the peak that is between 10 and 20 seconds for the input corresponds to the peak between 10 and 20 seconds for output A. But generally speaking, these two signals are not in phase. There is generally an angle between the two. So in other words, output A can lag or lead with respect to the input. Now let's take a look at output B, that is the marginally stable system that has a couple of poles on the imaginary axis. However, these two poles do not coincide with the poles of the input. So here the output is a superposition of two harmonic functions, one that has the main curve, the main sinusoidal has the same frequency as the input, but there is superimposed another sinusoidal with a higher frequency, and that is the frequency, the natural frequency of the two poles of the system. Then for output C, we have that when we excite the system with the same frequency of the same natural frequency of the system. So in other words, the poles of the input are the same as the pole of the transfer function plant, or the plant transfer function, then the system's response oscillates, yes, same frequency, yes, but the amplitude will tend to infinity. So we have an unstable system, or an unstable response, although the system itself is technically marginally stable. But again, there's marginal stability when combined with an input that has the same frequency, same natural frequency, what will cause the response just to blow up to infinity. The fourth case, so output D, is something that I haven't described earlier, but it's worth taking a look at it. So if you just take a look at the function in the time domain, it looks very, very close, very, very similar to output A. That is, we have just one sinusoidal, so one frequency, and that is the input frequency. And the amplitude has also changed. Here, the amplitude is about 2. But the thing here is that the whole curve has been transposed towards the positive values in the y-axis. And that is because of the presence of the pole at the origin. So that is the only consequence. When you have one pole at the origin, when you have one pole at the origin, the system will behave exactly like a stable system. So the response will have the same frequency of the input and will change the amplitude and the phase, but the overall response will be shifted. So the average value is not 0 anymore, but it's going to be a positive value or negative value, depends. But qualitatively, the output looks exactly like the output for case A. So from now on, we're going to consider systems that are either stable or, if marginally stable, have at most one pole at the origin. And so if you remember, this is exactly what we talked about when we introduced the final value theorem. So we're going to consider systems for which the final value theorem would apply. So all the poles on the left-hand side of the complex plane, or at most one pole at the origin. All right, let's go back to the notes. Right here is this just a description of what I've already said. You can have a response that is sinusoidal. So it's another harmonic function with the same frequency, but different amplitude and phase. And that happens if the transfer function for the plant is asymptotically stable, or you should add if it is marginally stable with at most one pole at the origin. Oh, there you go. I wrote it down here. See, forgot about it. Then for case B, we have a superposition of sinusoidal, and for case C, we have a divergent sinusoidal. So now let's take a look at a practical numerical example. So here we have the input that we just saw in MATLAB. So we have sine of 1/2 t. So the amplitude of this harmonic function is equal to 1, and the frequency is equal to 0.5 radians per second. Then we're going to do the following to this input. We're going to separate it in two branches. One branch will be multiplied by 2, and then it will be added to the same input, so the other branch, but the input this time is going to be integrated time-wise from 0 to t. This would be easier to do in the S domain, but we can also do it in the time domain. The only operations that you can actually perform when you're dealing with linear systems is multiplication by a scalar, addition, integration, or derivation. So let's build up the output. So we have 2 r of t plus the integral of r of t in dt. So r of t being sine of 1/2 t, we have 2 sine of 1/2 t minus, and now here we've solved the integral of sine of 1/2 t, which is minus 2 cosine of 1/2 t that has to be evaluated from 0 to t. And so we have 2 sine of 1/2 t minus 2 cosine of 1/2 t plus 2. And you see that this plus 2 is the fact that the output has been transposed in the y value by a constant. So we're suspecting here that in the S domain, we'll be able to find a pole at the origin for the transfer function. Now we can rewrite 2 sine of 1/2 t minus 2 cosine of 1/2 t, since the two harmonic functions have the same frequency, that is 1/2. We can use this trigonometric property. So if you have a sine of x plus b cosine of x, you can rewrite this as a sinusoidal whose amplitude is equal to square root of a squared plus b squared. So you take the square root of the amplitude of the first sinusoidal squared plus the amplitude of the cosinusoidal squared. And then you also have a phase shift, this angle phi, and this angle is going to be arctangent of b over a. Once again, just make sure that you calculate the correct angle based on the announcement that I made earlier today. All right, so in this case, we have that a squared plus b squared is equal to square root of 4 plus 4. So we have square root of 8. And then the phase that we are adding or subtracting is arctangent of -2/2. Oh, this is good because we can practice and we can see exactly which value for the arctangent we have to keep. So the numerator is the y coordinate. So the y coordinate being negative, we can either be on the third or on the fourth quadrant. But the denominator is positive, it's +2. So the x coordinate is positive. So y coordinate negative, x coordinate positive, we must be in the fourth quadrant. So if that is the case, you can just use your calculator and find arctangent of -1, which is -45 degrees or -pi/4. If we had been in the second or third quadrant, remember you have to add 180 degrees. So overall, the output can be written as a harmonic function, you see the sinusoidal, but the amplitude now is square root of 8, which is about 2.23. We have the same frequency, 1/2, but we have that the output is lagging by 45 degrees with respect to the input. And we also have that the overall output is shifted by 2 with respect to the y-axis. All right, now let's take a look at the same example, but in the S domain, and we will recognize exactly what's going on. So the input in the S domain, we've already seen, is 1/2 times 1 over s squared plus 1/4. Just recall that sine of AT is transformed into a over s squared plus a squared. G of s is quite easy to find because if we go back, we simply have 2, so a multiplier, and it's just a scalar, plus the integration operation. But integration in the S domain is 1 over s. So G of s is simply 2 plus 1 over s. Now, if we want to have just one fraction, that is going to be 2s plus 1 over s, or 2 times s plus 1/2 over s. And that is exactly the system that I considered in case B in MATLAB. So we have 1, 0 at -1/2, kind of irrelevant for the stability purpose. And we have 1 pole at the origin, making the system marginally stable. So please modify here. It's not stable as in asymptotically stable, but it is marginally stable. So having 1 pole at the origin, we expect the output to be a sinusoidal with the same frequency as the input, but it's shifted by a constant. And in this case, the constant is +2. All right, once we have the output, which you obtain by, as usual, multiplying the transfer function of the plant by the input, and if you take the inverse Laplace transform, you can find the function in the time domain, which is exactly what we found earlier. That is 2 plus square root of 8 times sine of 1/2 t minus 45 degrees. We're not going to focus on two things. We're going to focus on the amplitude ratio, so the amplitude between the ratio between the amplitude of the output, that is AF, amplitude final, and the amplitude of the input, which I've been calling A naught. So we can see whether the system shrinks or enlarges the amplitude of the input. In our case, the amplitude for the output is equal to square root of 8, whereas the amplitude of the input is 1. So the signal has been increased in amplitude by a factor of square root of 8. Now, usually, instead of just taking the amplitude, we take the 20 logarithm in base 10 of such amplitude. And the units for 20 logarithm in base 10 of something are decibels. So how much the amplitude has been increased or decreased is measured in decibels. In this case, we have 20 logarithm of square root of 8 is equal to 9.03 decibels. And the other thing that we will focus on is the phase difference between the input and the output. And that is that angle phi that we saw right here. So that is the difference in terms of phase between the harmonic function that describes the input and the harmonic function that describes the output. In this case, we have a phase difference of minus 45 degrees. And remember that this is valid for an input frequency of 1/2 radians per second. So in fact, what we can do, we can plot 2 points here corresponding to omega equals 0.5. We have, in terms of the amplitude ratio, at 9.03 decibels. And then we have a phase difference of minus 45 degrees. So we have 2 points. And here I indicated in purple. Well, once again, this is valid only when the input and the output frequency is equal to 1/2. What if we changed such frequency? Would the amplitude ratio be the same? Would the phase difference be the same? Well, the answer is no. In general, they would change. And so we would have to repeat the same process by changing the input frequency. Let's say we take 1 radian per second, and then we would have to compute the output, find the amplitude, take the ratio between the final and initial amplitude, compute the 20 logarithm of such ratio, and then find another value to plot. Same thing for the phase. And so once you have all these points, you can find curves such as this. Here, dashed curves for the amplitude ratio and for the phase difference. Well, these plots are called the Bode plots. And so you see we have one plot for the amplitude, or again, it should be for the 20 logarithm of the amplitude ratio. And then we have another plot for the phase difference between the output and the input. So on the y-axis, we have on the first subplot decibels, and in the second subplot, well, we have the phase that generally is measured in degrees. What about the x-axis? Well, on the x-axis, we have the input frequency. Now I'm just going to call it frequency because the input and the output frequency are going to be the same. So on the x-axis, we have the frequency. And normally we use a sort of a semi-logarithm scale on the x-axis. so that equal intervals are not linearly equal, but the ratio between the two marks are the same. For instance, here we have 0.01 radians per second, and then the next mark we have 0.1. And if we use the same space, we get to 1, and then 10, and so on and so forth. So the distance between marks is called decade. And decade actually is because if you take the ratio between the upper value with respect to the lower value, well, the ratio is equal to 10. For instance, 0.1 over 0.01 is 10. So there's a decade between 0.01 and 0.1. Same thing, for instance, if we take the interval of frequencies between 1 and 10, the ratio is going to be higher, the higher value, that is 10, over the lower value, that is 1. So 10 over 1 is once again 10. You can see here that obtaining these Bode plots by repeating all the calculations for each frequency would be crazy. It's very inconvenient. It's sort of the same thing. It's the same concept that we saw for the root locus. Technically, you could find the root locus by changing the values of k and then computing the closed loop poles, and then change the value of k, recompute the closed loop poles. So you have a bunch of points, and then when you connect all the points, you find the nice root locus branches. But we found a way to draw them without having to do such a routine. So we're going to find a way to create the Bode plots without having to do all the calculation over and over again. So that's exactly what we're going to see. And in order to find the Bode plots, all you need is your system transfer function, because the input might be different. The Bode plots will take care of any kind of sinusoidal inputs, because you can vary here the frequency. And so based on the frequency and on whatever amplitude the input has, the Bode plot will tell you, well, the ratio between the final and the initial amplitude. So if you have such ratio and the initial amplitude, you can comfortably compute the final amplitude. And then you can see how much the output is shifted with respect to the input. So the amplitude ratio is very simply just the magnitude of the transfer function of the system. That's as easy as that. And the phase change is the phase associated with the transfer function of the system. So normally you have the transfer function of the system. So we know how to compute the magnitude of a complex number. We know how to compute the phase. And so we're going to have the amplitude ratio and the phase change. Now there's a caveat here, and that is that the transfer function, which is normally a function of s, and s is normally well, here probably I should use another pen. All right, draw. There we go. So normally S has a real part plus an imaginary part. So it's sigma plus I omega. However, here we're only interested in I omega. And why is that? Well, that is because sigma, the response associated with the real part of a complex number, if you remember, is associated with the exponential function. So since we are dealing with stable systems for the most part, then e to the minus sigma t, well, just goes to 0 for when time goes to infinity, or for the steady state portion of the response. So really the only factor that will remain is I omega. It is the oscillating part of the response, and that's exactly what we have. So what we need to do, and that's exactly what we're going to see right now, you take there you go. You take your transfer function. For our example, that was 2 times s plus 1/2 over s, and we substitute s equals I omega. So now our transfer function is not a function of s anymore, as in a complex number with both real and imaginary part, but it's simply a function of the frequency omega. So g of I omega is equal to 2 times I omega plus 1/2 over 1/2. All right, so let's actually find out that the ratio, 20 logarithm of the ratio of the amplitudes, is 20 logarithm of the magnitude of the transfer function, as I stated. But that was just a statement. Now let's prove that that is indeed the case. So what is the magnitude of g I omega? Well, we have a complex number here with the numerator and a denominator. So the magnitude of the numerator is, well, 2 remains 2. So that is fine. But then the magnitude of I omega plus 1/2, we have square root of real part squared, so 1/4, and then imaginary part squared, which is omega squared. At the denominator, instead, we have the magnitude of I omega, which is simply omega. Now here I've just used the properties of logarithm to break down this fraction. So review properties of logarithm if you don't remember them. And so we're left with this function here, which is a function of omega alone. Now let's check that for omega equals 1/2, we indeed get the 9.03 decibels that we found earlier. If you substitute omega equals 1/2, well, that's exactly what you get. You have 20 logarithm of 2 plus 20 logarithm of 1/2 minus 20 logarithm of 1/2. So these two terms will just reduce to minus 10 logarithm of 1/2, which is also 2 to the power of minus 1. And so we are left with 30 logarithm of 2, which is 9.03 decibels. That's exactly what we were expecting. Now let's find the phase difference between the output and the input by computing the phase of the transfer function. Let's go back again. Let's take a look at the transfer function. So phase associated with 2, well, 2 is a positive real number, so we simply have 0. Then we have the phase of the numerator of this fraction. So it's going to be arctangent of imaginary part, that is omega, over real part, that is 1/2, minus arctangent of imaginary part of the denominator, which is omega, over real part, which is 0. And that's exactly what we have here. We have arctangent of 0 over 2, which is 0, and then arctangent of omega over 1/2 minus arctangent of omega over 0. Now, omega is a frequency, therefore it is a positive number. 0, well, it's just 0. So here, arctangent of plus infinity is 90 degrees. So the function that we're left with is arctangent of 2 omega minus 90 degrees. And this is valid for all values of the frequency that is greater than 0. Now let's check what we have for omega equals 1/2, like in our example. When we're left with arctangent of 2 times 1/2, or arctangent of 1, so it's 45 degrees, minus 90, and so we have minus 45 degrees, and that checks exactly with what we had. Okay, I'm gonna stop here for now, and I'm gonna continue in the second part. So I'll see you in part 2.